So this week we're going to talk about computational complexity. And this is going to be, we are going to do some rigorous maths this week, but this is probably going to be the most kind of philosophical week of lectures in this module. But yeah, like I said, especially tomorrow and on Wednesday, there's going to be some like actual maths, but today is going to be, well, there might be a little bit of real maths today, but a lot of it's going to be about kind of philosophy about kind of problems and complexity of problems. So for this week, I'm not going to follow the notes of Shriver. So I've got there's a link to some notes and also a video, basically a video of a lecture which I'm from MIT, which I'm basically going to kind of copy in this lecture. But if you want to hear it from somebody else, then you can look at this video. So the notes, the Shriver notes, they do talk about computational complexity. It's a little bit more technical than what I want to do this week. I think it's better to have a kind of, perhaps it might be a little bit less rigorous than what is done in the Shriver notes, but I think it's going to be good enough for our purposes so that we don't get bogged down with like defining what an algorithm is rigorously and things like that. I think we sort of have an intuitive idea what these things are, and that's going to be good enough. So the type of questions we're going to be looking at this week are, what does it mean for a problem to be hard? And also, can all problems be solved? And that sort of. Now, so most of the modules so far, we've looked at a bunch of different mathematical problems. For most of them, I've given you polynomial time algorithm, right? Which may give you the impression that, maybe all problems can be solved in polynomial time or something, right? Or at least you might think that all problems can at least be solved. But basically the message today is that the universe is not so kind. There's a lot of problems which you can't even, there doesn't even exist an algorithm to solve them. But at the end, I'll mention that actually this can sometimes work to our advantage. Okay, so let me start with some definitions. And these definitions are going to be, again, kind of maybe not the most rigorous way you could possibly define these things, but it should be at least, kind of intuitively clear what I'm talking about. So we're going to define complexity classes of problems. So P is a set of all problems which can be solved in polynomial time. Who here has heard of P? And what about NP? Okay, so yeah, good. Right, so and when I say polynomial time, right, this basically means, so if the input of your problem has size n, this is time big O n to the c for some constants, right? That's what polynomial. Okay. Does anyone who has heard of x or x? Well, it's kind of okay from how it's written. It's maybe guessable. So this is problems which can be solved exponential time. Where when I say exponential time, what I mean is something like 2 to the big O n to the c for some. So it's exponential in perhaps some polynomial of the input size. And like the main focus of this module, right, from the very beginning, what we've been talking about is basically, like most examples of problems we looked at are clearly in X, right? So for example, if you wanted to find the biggest matching in a bipartite graph, you can easily do this in exponential time by just kind of checking every possible set of edges and seeing if it's a big matching, right? And so the focus really is we take problems which are obviously in X and we show that they're in P. That's been kind of the focus so far. So most of this module focuses on taking problems that are obviously in X, because you can have some sort of not even a very clever algorithm just by checking all the possibilities and showing they are in P, right? By doing something more clever, faster kind of algorithm. Okay, and obviously, one thing, should be clear, right? That P is a subset of X, right? Because generally, an exponential function is bigger than a polynomial function. Okay, and now R. So this is not really a commonly used class of problems, but it's useful to talk about them in this lecture. So this is the set of all problems that can be solved in finite time. So this is basically the set of all problems for which there exists some algorithm, even if it's really slow, really really bad algorithm, but eventually you can get to the answer, in finite amount of time. And of course, P is a subset of X, like we said, which is a subset of R, right? Any questions about these definitions? So if you look at it, right, so if you kind of think of it on a line, right, if this is if you kind of order all the problems in order of, let's say, if you kind of take all the problems in the universe and you order them on a line where they're in order of increasing, let's say, difficulty. So I'm not going to use the word complexity because it's kind of a kind of technical term that has a real proper definition, whereas it's better to use a kind of vague term in this for the purposes of this. But yeah, so basically you have your problems in P, you have X, and you have R, right? So if something is in P, so these are kind of the problems are getting harder and harder as I go this way. And then there's going to be something else, well, NP, which I haven't just defined yet, but I'll define in a little bit. And a natural question is, does there exist any problems out here? That's one thing that we're going to address in a few minutes. So it turns out that actually, so these are basically all the problems you can solve, up to this point. There are lots of problems that you can't solve. That's kind of a spoiler. Okay, so examples of problems, right? So there's lots of problems we've seen. So find the max matching in a bipartite graph. Okay, so can anyone tell me which class this belongs to? P, X, well, I guess if it belongs to one of them, then it belongs to all the ones that come, but this is something we've given algorithm, polynomial time algorithm to do this already, right? So this is in P, and so here's a problem which is not in P. So hopefully everybody knows the game checkers, right? So checkers on an n by n board. So the board is going to infinity, or the board is n by n. And what do I mean by what is the problem? So the problem is to determine if there exists a guaranteed winning strategy from your current position. Right, so if I give you like a big checkerboard and I give you a current position for checkers, you can ask, okay, is there a guaranteed winning strategy from this point? So this is in X, because basically you could sort of just go through all the possible strategies and you could work out if one of them guarantees you to win, but it's not in P. So that's an example which, so the first problem here was, it's in P, and the second problem is somewhere over here. Another nice example is the halting problem. Okay, so this one says, so given a computer program, so it doesn't matter what language it's in, C or Python or whatever, it doesn't matter. But so somebody gives you a computer program and you want to determine, does it ever terminate or halt? So somebody gives you a computer program, you want to decide, is this thing going to run forever or does it eventually stop? Is it clear what the problem is? And this one turns out to be, this third problem is not in R. So it's not solvable in a finite amount of time. So this problem is somewhere over here. So when something is not in R, we call this an undecidable problem. Any questions about that? So this is actually an example, I think, of something which actually could have practical applications, right? So, I mean, in theory, somebody, if you're running some algorithm and it's taking a long time, you might want to actually know, is this thing ever going to end? And this tells you that, okay, there's no algorithm which, given any program, can actually tell you if it's going to end or not, which is kind of a, you could actually want such a program, but it doesn't actually exist. There's no way to do it. And that's not something we're going to to cover in this module, but I mean, we're not going to prove this, but we are going to prove that there are undecidable problems. Another one, coming back to things that we've talked about in the module, so given a graph G, does G, or does there exist, or yeah, does G have, oh, sorry, suppose I take a graph G and an integer k in the naturals, does G have a vertex cover of size at most k? So remember, a vertex cover is a set of vertices that hits all the edges, right? This is something we were talking about in week 3. And this turns out to be something called NP-complete, which we'll discuss in a bit, but in some sense, it lies. So this sort of is the way you can rank these problems into difficulty. Okay. So now let's do something rigorous. But are there any questions about anything I've talked about so far? So now I'm actually going to, I'm going to define something and then I'm going to prove something for you. It's going to be a rather kind of simple proof. Okay, so for some kind of technical reasons, okay, so a lot of the problems we've talked about so far, in previous weeks have been like, find the biggest matching in a bipartite graph, or find the smallest vertex cover or the largest flow, these sorts of things. This week we're going to focus more on something called decision problems, okay, but all of these things can sort of be turned into decision problems in some sense. So let me explain what I mean by that. So a decision problem is a problem, of course, where the only possible outputs are yes and no. Okay. Sometimes, okay, yes or no is the same as kind of, I mean, if you were a computer, you might prefer, rather than yes or no, you might prefer 0 or 1, right? Where 0 is no, yes is. Okay, so I mean, these sorts of things, it is very related to what we've been doing, right? So rather than asking, say, does a graph have or what's the biggest perfect matching or biggest matching in a bipartite graph? Instead, what you can ask is, you can pick a number k and say, is there a matching of size at least k, right? So kind of, so in some sense, kind of all optimization problems can be phrased as decision problems. Or at least it could be a sort of sequence of decision problems. So, for example, rather than asking for the biggest matching, you can ask, first, is there a matching of size at least 1, right? And then you can ask, is there matching of size at least 2, and so on and so forth until you get a no, right? And then you found the biggest matching. So in some sense, all of these things we've been doing, you can turn it into a decision problem, and it's going to be more convenient to talk about decision problems rather than general optimization problems. Is it clear what I'm saying here? So for the rest of this week, basically every problem has either a yes or no answer whenever I say, whenever we're talking theoretically about problems. Okay, so here's the theorem. This is going to be sort of not the most technically stated theorem, but hopefully you'll get the idea. So most decision problems are undecidable. And, okay, it's not clear perhaps what I mean by most, but in the proof it'll hopefully be clear. Right? And this sounds like really bad news, right? So, I mean, our whole goal in this module is to find algorithms to solve things. And this is saying basically most problems that exist, you don't have a chance to find an algorithm. There just isn't an algorithm at all. There's no chance. Okay, and the proof is simple. Basically, it's just sort of some basic set theory. Okay, so here's the first thing we need to address. So how many algorithms are there? And I mean this in a theoretical sense. So how many possible algorithms are there? Okay, obviously the answer is sort of infinity, right? But I want to know what kind of infinity, right? In terms of countable, uncountable, that sort of thing. Well, what is an algorithm? So if you think of it like a computer program, right? It makes things a bit more concrete. And what's a computer program? It's just a bunch of stuff you write into the computer, right? It's a bunch of symbols, right? It's a finite set of symbols, essentially. It's a finite list of symbols. And, well, all of these symbols, of course, could be converted, for example, into binary. So it's really, so if you convert, so when I say symbols, I mean like letters and stuff, right? You write, 4, I equals, just literally, you write stuff, right? So you can convert these symbols. So as you know, probably the computer, right, when it takes a computer program, it converts everything to binary. And so therefore, what a computer program is, so a computer or an algorithm, well, yeah, let's say a computer program is a finite binary sequence. And so if you take a finite binary sequence, well, you can also convert that into a number. So you can convert this, every finite binary sequence corresponds to a natural number. Okay, so this is a lot of writing just to say that the number of algorithms is countably infinite. So the set of all algorithms is the same as the cardinality of the set of all algorithms is the cardinality of the natural numbers, which is all if not. Okay, but now we have to ask how many problems are there. So we've kind of counted all the algorithms. Now let's count the problem. Well, when I say problem, I mean decision problem. So what is a problem? A problem basically takes a bunch of inputs and it associates each of them to either yes or no. So a problem is a function from a set of input structures, which could be, for example, graphs or, for example, numbers, natural numbers, and so on. But we don't have to get really technical with what we mean by input structures. But it's a function which maps input structures to either yes or no. So let's think of the input structures as natural numbers. So think of the set of input structures as being just the natural numbers. I mean, basically, it has the same cardinality as, for example, the set of all graphs or whatever. So it doesn't really matter. And think of, so this tells us that the set of all problems has cardinality the same as the set of all functions from natural numbers to, let's say, 0, 1, right? Because, of course, yes and no can just be written as 0 or 1. And, so this is the set. So these can be thought of as infinite binary sequence. And this has the size, the cardinality of the real 1, which is bigger than aleph naught. To see that infinite binary sequences has the same cardinality as the reals, you can, for example, so for every real number, you can look at its binary expansion and associate that to an infinite binary sequence, and vice versa. Okay, so there's way more problems than there are algorithms. So therefore, maybe I should just say, therefore, every algorithm can only solve at most one problem. There are way more problems than algorithms. So therefore, almost all problems have no algorithm that solves it. I know that's a bit, maybe not the most rigorous kind of argument, but hopefully you can get some idea. Any questions about that? Okay. But obviously most of these problems are going to be really, pathological kind of things that nobody would ever want to solve, right? But technically they're, but then you also have some interesting problems which are unsolvable or undecidable, like the halting problem. So there are actually interesting problems which we can't solve, and there's a lot of pathological ones. Now we want to talk about NP. Right, so NP is a kind of a strange collection of problems. There's different ways to define NP. In the notes that I've given you the link for in the Moodle page, it's actually defined a little bit differently, but it all turns out to be equivalent to what I'm going to say now. And this is the definition that really you're going to need to remember. So NP is the class of decision problems such that, there exists an algorithm which can check, a certificate for a yes instance in polynomial time. So what do I mean by a certificate? So a certificate for a problem is a kind of structure which certifies the answer. That the instance you're looking at is a yes instance. So I understand this sort of sounds weird, so let me give you an example. to illustrate it. So for example, the problem of deciding whether a graph has a vertex cover of size at most k, that's in MP. So the problem of deciding if G has a vertex cover of size at most k is in MP. Okay, and why? Right, because there exists an easily checkable certificate for this problem, right? So the certificate is a set, S, a subset of V, and so if somebody gives you a subset of the vertex set, you can check quickly whether it satisfies the condition. So Ken can easily check whether, first of all, S is a vertex cover, and secondly, you can obviously easily check if the size of S at most. When I say easily, you can check it in polynomial time. You can just literally go through every edge in the graph and check, is one of its endpoints in S. You can do that in polynomial time, and so therefore this is a certificate that can be checked in polynomial. And obviously you can just count the elements in S, 1, 2, 3, 4, up to k, check that it has size at most. Yeah. I mean, basically the point is, if somebody gives you a subset of the vertex set and tells you, they give you their word, this is a vertex cover, you can easily check if they were lying, right? And it doesn't take you very long to check. That's the point. Any questions about this definition? I know it's a little bit philosophical, all of these things. Oh, and by the way, it's important here in this definition of NP that we're only talking about that there exists a certificate which can prove a yes instance. So if somebody gives you a graph, there's a certificate that can show easily that there's a small vertex cover. You just give them a vertex cover. But there's not necessarily a certificate showing that there isn't small vertex cover. Okay, so there's actually another complexity class for that. So the co-MP, similar to NP, so it's a complexity class, but every no instance has a certificate. So I'll be a bit informal here, but I'll just say as a polynomial time checkable certificate. Basically, if you have a problem which is an NP and you kind of change it, kind of negate the question you're asking, it becomes something co-MP. So I can say, if I ask the question, given a graph G and integer k, is it true that G does not have a vertex cover of size at most k? That gives you a problem which is in co-MP. Yeah, it's sort of the opposite of a problem. But it's important to get the difference between these. Now, okay, so yeah, just a note. So this is because this is a kind of mistake people make a lot. NP does not stand for not polynomial. Okay, what it really means is, so NP is something called non-deterministic polynomial time, which is a kind of technical term. You don't really need to know what it really means, but yeah, so it definitely does not stand for not polynomial. So some of you may have heard of, so one thing that's somewhat clear is that any problem which is in P is definitely in NP, right? So P is a subset of NP, right? And why? Because, if you have a problem which is in P, you can actually completely solve it in polynomial time. And solving it sort of also includes kind of certifying that your answer is correct, right? So if you can completely solve the problem in polynomial time, in some sense, the problem itself is a certificate, that it's a yes instance or a no instance. So in fact, P is in NP and it's also in co-NP. A problem, this is an open problem, so nobody knows so far whether P is equal to NP or not. So if you solve it, so a solution is worth, you may have heard of these millennium problems. So this is one of the millennium problems, and the solution is worth $1 million. So if you can solve this, the Clay Maths Institute will give you $1 million. perhaps I should have put this on an exercise sheet or something, and if you thought you could solve it, maybe you just would. Right? But yeah, so this is like one of the biggest open problems in all of computer science, also as well as mathematics, and yeah, it'd be a big deal if you can solve that. And well, of course, since we don't know the answer technically, it could be the case that P is equal to MP. Nobody knows, but it seems very unlikely. And the kind of philosophy here is basically just that, being able to check your answer should be easier than being able to completely solve a problem, right? Checking an answer should be usually easier, strictly easier than solving a problem, but we don't know. Yeah, so now, okay, so I'm going to just end with a definition, and we're going to continue next time, tomorrow, starting with this definition. But so a problem is said to be NP hard. So this is going to be a kind of informal definition if it is at least as hard as any problem in NP. What does that mean, right? And we're going to give a more formal definition tomorrow. But basically, the idea is, the kind of idea is, a problem is NP hard if you had basically an algorithm to solve it, you could use that, you could adapt that algorithm to solve anything in NP. So if you had an algorithm to solve it, then this algorithm could be used to solve anything in NP. Or let's say that this algorithm could be converted to an algorithm to solve any problem in NP, which is a really weird concept. It seems like very unclear that, why should there even be such a problem? But we're going to see tomorrow and Wednesday that there's a lot of the problems we've already seen, like vertex cover problems and things like that. Those turn out to be NP hard problems. Okay, so that's it for today.